Welcome to this deep dive into Kubernetes Gateway API YAML examples. Today we'll examine the structure and components of Gateway class. Gateway. An HTTP route manifests in detail. Gateway API consists of three primary resources. Gateway class. Gateway. An HTTP route. Each serves a specific purpose in the traffic management architecture. In a Kubernetes cluster, Gateway API resources form a hierarchical structure. At the top is Gateway class, which is cluster scoped and defines gateway templates. Below that are gateway resources, which are namespaced and represent actual load balancers. Finally, we have route resources like HTTP route that define specific routing rules. The gateway class is a cluster-scoped resource that defines a class of gateways with common configuration and behavior. Controllers implement gateway classes to provide specific functionality like load balancers or service mesh gateways. The gateway is a namespaced resource that represents a load balancer operating at the network edge. It implements the configuration specified in the gateway class and provides an actual load balancer, or proxy for routing traffic. The HTTP route is a routing resource that specifies how HTTP traffic should be forwarded from the gateway to Kubernetes services. It contains matching rules, header manipulations, and traffic splitting capabilities. At the bottom we have our applications that receive traffic routed through the gateway and HTTP route resources. The gateway acts as the traffic entry point, directing requests to the appropriate services based on the routing rules. This hierarchy provides a clear separation of concerns. Gateway class defines what type of gateway to create. Gateway implements that configuration. An HTTP route specifies how traffic should be routed to applications. With this understanding of the resource hierarchy, let's dive deeper into each resource and examine their YAML manifests in detail. Let's start with Gateway class, which defines a class of gateway that may be requested by users. It's implemented by a controller that provides specific functionality. Let's examine the Gateway class YAML manifest in detail, breaking down each section to understand its purpose and configuration options. The API version field specifies which version of the Gateway API to use. In this case, we're using v1 beta 1, which is the current beta version of the Gateway API. The kind field specifies the type of Kubernetes resource. For Gateway class, this must always be Gateway class. The metadata section contains identifying information about the resource. The name field is required and must be unique within the cluster since Gateway class is a cluster-scoped resource. The spec section contains the detailed configuration for the Gateway class. The controller name field is required and specifies which controller is responsible for implementing gateways of this class. This could be a cloud provider's load balancer controller or a service mesh gateway controller. The parameters ref field is optional but powerful. It allows you to reference additional configuration parameters that customize the behavior of gateways created from this gateway class. These parameters are defined in custom resources specific to the controller implementation. In summary, Gateway class acts as a template that defines what type of gateway to create and how it should behave. Controllers implement gateway classes to provide specific functionality such as load balancers or service mesh gateways. Next, let's examine the gateway resource, which represents a load balancer operating at the network edge. It receives traffic from outside the cluster and forwards it to services. Now let's examine the gateway YAML manifest in detail, breaking down each section to understand its purpose and configuration options. The API version field specifies which version of the gateway API to use. Like gateway class, we're using v1 beta 1. The kind field specifies the type of Kubernetes resource. For gateway, this must always be gateway. The metadata section contains identifying information about the resource. The name field is required and must be unique within the namespace. The namespace field specifies which namespace this gateway belongs to. The spec section contains the detailed configuration for the gateway. The gateway class name field references the gateway class that defines the template for this gateway. This establishes the connection between the gateway and its implementation controller. The listeners field defines the network listeners for the gateway. Each listener specifies a port, protocol, and optional TLS configuration. Listeners are how the gateway receives traffic from outside the cluster. In this example, we have two listeners, one for HTTP on port 80 and one for HTTPS on port 443. The HTTPS listener includes TLS configuration with terminate mode, which means the gateway terminates TLS and forwards decrypted traffic to services. In summary, gateway represents a load balancer operating at the network edge. It receives traffic from outside the cluster and forwards it to Kubernetes services. The gateway implements the configuration specified in the gateway class and provides an actual load balancer or proxy for routing traffic. Finally, let's look at HTTP route, which specifies how HTTP traffic should be forwarded from a gateway to Kubernetes services. It contains matching rules and routing configurations. Finally, let's examine the HTTP route YAML manifest in detail, breaking down each section to understand its purpose and configuration options. The API version field specifies which version of the gateway API to use. Again, we're using v1 beta 1. The kind field specifies the type of Kubernetes resource. For HTTP route, this must always be HTTP route. The metadata section contains identifying information about the resource. The name field is required and must be unique within the namespace. The namespace field specifies which namespace this HTTP route belongs to. The spec section contains the detailed configuration for the HTTP route. The parent refs field specifies which gateway or gateways this route should be attached to. This establishes the connection between the HTTP route and the gateway that will implement its routing rules. The rules field defines the routing rules for the HTTP route. Each rule contains matches that specify when the rule should be applied, and backend refs that specify where the traffic should be sent. Rules are evaluated in order until a match is found. In this example, we have two rules. The first rule matches requests with paths starting with API and splits traffic between two services. API service gets 80% of the traffic and API canary service gets 20%. This is useful for canary deployments. The second rule matches requests with paths starting with web and sends all traffic to web service. This demonstrates simple path-based routing where different paths are directed to different services. In summary, HTTP route specifies how HTTP traffic should be forwarded from a gateway to Kubernetes services. It contains matching rules for traffic routing, header manipulations, and traffic splitting capabilities. HTTP routes can be attached to gateways to define specific routing behavior for HTTP traffic. Now let's understand how these resources work together in a complete Gateway API implementation. Let's visualize how Gateway class, Gateway, and HTTP route resources work together in a complete Gateway API implementation. The relationship between these resources is hierarchical and explicit. Gateway class defines what type of gateway to create and how it should behave. Gateway implements that configuration in a specific namespace. HTTP route specifies how HTTP traffic should be routed from the gateway to services. This clear separation of concerns makes Gateway API more flexible and powerful than traditional ingress, allowing for more sophisticated traffic management patterns. Let's put it all together with a practical example showing how these resources interact in a real-world scenario. Let's look at a practical example that demonstrates how these resources work together in a real-world scenario. Imagine we're deploying a web application with an API backend and a front-end web interface. External traffic flows from the internet through a load balancer to the gateway. The gateway implements the configuration specified in the gateway class. The HTTP route defines how traffic should be routed to our services based on request paths. Requests to paths starting with API are routed to the API service, while requests to paths starting with app are routed to the web service. This demonstrates path-based routing, one of the core capabilities of Gateway API. This example shows how Gateway API enables sophisticated traffic management patterns that are difficult or impossible to achieve with traditional ingress resources. Gateway API also supports advanced configuration options that provide powerful traffic management capabilities. Gateway API supports many advanced features that provide powerful traffic management capabilities. Let's look at some of these features with examples. This advanced HTTP route example shows several powerful features. The hostnames field specifies which hostnames this route applies to, allowing for hostname-based routing. The first rule demonstrates header-based matching and request header modification. Only requests with the exact header role equals admin will match this rule, and those requests will have an X-role header set to admin before being forwarded to the admin service. The second rule shows timeout configuration. Requests have a 10-second timeout overall, and back-end requests have a 5-second timeout. This helps prevent hanging requests and improves application reliability. Another advanced feature is traffic splitting. which allows you to distribute traffic between different service versions. This is particularly useful for canary deployments and A/B testing. In this traffic splitting example, 90% of requests to the API path are sent to the stable service version, while 10% are sent to the canary version. This allows you to gradually roll out new features while monitoring their performance and stability. In summary, Gateway API provides many advanced features including hostname-based routing, header-based matching, request-response filtering, timeout configuration, and traffic splitting. These features enable sophisticated traffic management patterns that are essential for production environments. In summary, Gateway API provides a powerful, extensible approach to traffic management in Kubernetes. The Gateway class, Gateway, and HTTP root resources work together to create a flexible and robust traffic routing system. Thank you for learning about Gateway API YAML examples. Understanding these manifest structures will help you implement sophisticated traffic management solutions in your Kubernetes clusters.